All right, today we're going to pull back the curtain on one of science's most precise measurement tools. We're going to explore the incredibly clever engineering that's hidden deep inside the ionization chamber, a device built to measure the invisible world of radiation with, well, just stunning accuracy. Ready? Let's get into it.
So think about this for a second. This is the fundamental challenge. Ionizing radiation, things like X-rays or gamma rays. You can't see them, you can't feel them, you can't hear them. But in fields like medical physics or nuclear safety, measuring it with precision is literally a matter of life and death. So how in the world do you measure something you can't even perceive? That's the exact problem we're going to solve today.
Okay, so here's our game plan. We'll kick things off with the basic measurement challenge. Then we'll look at a simple idea that seems great, but is actually deeply flawed. From there, we'll uncover the elegant engineering solutions that make these things work so well, and by the end, you'll understand the complete anatomy of accuracy.
The basic idea here is actually pretty beautiful and simple. When radiation zips through the air inside this chamber, it has so much energy it literally smacks electrons right off the air molecules. This creates what's called an ion pair. You get a free, negatively charged electron and a now positively charged atom. And here's the trick. If we can just collect all those charged particles, we create a tiny electric current that tells us exactly how much radiation is there.
So let's build one in our minds, right? The most basic version. You've got a sealed box full of air. In the middle, there's a metal rod. That's our collector. The outer wall of the box acts as the other electrode. Then you apply a high voltage between the wall and the rod. In theory, that electric field should just suck all the positive ions to one side and all the negative ions right to our collector. Simple, right? Well, not so fast.
Yeah, so in the real world, that beautifully simple idea, it would fail. And not just fail a little bit, it would fail spectacularly. And to really get why, we need to understand the scale of what we're trying to measure. And here's the thing. The current that the radiation creates isn't just small. It is almost unimaginably faint. I mean, we are talking about a tiny, tiny whisper of a signal in a world that is just full of electrical noise and shouting. This extreme weakness makes our measurement just incredibly vulnerable to any kind of interference. I mean, just get a load of this number. 10 to the minus 14 amps. That's a femtoamp. It's 1,000,000 times smaller than a billionth of an amp. Trying to measure this is like trying to hear a pin drop in the middle of a Metallica concert. It's almost impossible. Any other tiny bit of electrical noise will completely drown out the real signal we're trying to find. And this brings us to the main villain of our story, an electrical noise source called leakage current. It's the arch nemesis, the enemy within, that threatens to make our entire measurement completely useless. So here's the deal. No insulator on Earth is perfect, period. You've got this high voltage on the outer wall, and our super sensitive collector is sitting right next to it, separated by what we hope is a good insulator. But a tiny, unwanted current will always try to leak across that insulator and go straight to our collector. And this leakage current is often thousands of times stronger than our real signal, completely contaminating our data. But this is where the story gets really good. This is where some absolutely brilliant, elegant engineering comes in and saves the day. So let's introduce the heroes of our design, the components that are specifically built to defeat this leakage current. So, say hello to our hero, the guard electrode. It might not look like much. You can see it here. It's just a simple metal ring. But its function is pure genius. It's placed strategically right between the high voltage source and our signal collector, and it acts as a kind of bodyguard for our measurement.
Okay, now this is the really clever bit. This is the magic. The guard is kept at the exact same voltage, the same electrical potential as the collector. Now, because there's no voltage difference between the guard and the collector, there's absolutely zero electrical pressure for current to leak between them. It's like trying to get water to flow between two ponds that are at the exact same height. It's just not going to happen.
Let's trace the path here. It makes it super clear. You've got high voltage on the outside wall. The leakage current tries to sneak across that insulator to get to our collector. But the guard electrode is waiting for it. It acts like a moat around a castle. It intercepts all of that nasty leakage current and shunts it safely away to ground, leaving our collector completely untouched, measuring only the pure true signal from the radiation. It's brilliant. Okay, so we've solved the leakage problem. We're done, right? Nope, not even close. For a truly accurate measurement, you don't just need a clean signal. You need to know exactly what volume of air that signal came from. And as it turns out, our hero, the guard electrode, has a second, equally important job. See, if you don't have a guard, the electric field gets sloppy.
It bulges out at the edges of the collector, kind of like you see here in these diagrams. And that distortion means you're accidentally collecting ions from a region outside your intended measurement volume. So your true collected volume doesn't match your nominal or calculated volume. You think you're measuring a coffee cup's worth of air, but you're really measuring the cup plus a little extra all around it. Your whole measurement is just wrong.
So this little guard electrode is a total multitasking genius. First, it's a bodyguard, intercepting all that leakage current. And second, it's a stencil. It shapes the electric field, forcing the field lines to be perfectly straight and uniform, right to the very edge of the collector. It precisely defines the boundaries, guaranteeing that the volume we measure is the exact volume we think we're measuring. No more, no less.
All right, let's put it all together now. We can finally look at a complete modern ionization chamber and see how all these incredible principles combine to create an instrument of just unbelievable precision. And here it is. This is a classic farmer-type thimble chamber. You'll find these in hospitals all over the world, and it's a perfect example of everything we've just talked about. You can see all the parts: the outer wall, or the thimble, the central collecting electrode made of aluminum, and then nestled right in between, the crucial insulator and guard electrode assembly that makes the whole thing work.
So let's do a quick rundown. You've got the thimble wall, usually made of graphite because it's air equivalent. It responds to radiation just like air does. Then there's the central electrode, made of aluminum, designed purely to collect that tiny, tiny current. The insulator, often a special plastic, provides that critical electrical separation. And of course, the guard electrode, doing its two vital jobs, blocking leakage and defining that collection volume with absolute precision.
And this really gets to the heart of it, doesn't it? The incredible accuracy of this entire device. It doesn't just come from the obvious parts you see first. It hinges on these clever, often overlooked details, like the guard electrode. It's the unseen component that guarantees the integrity of the entire measurement.
So that kind of leaves us with a bigger question, doesn't it? We rely on data for pretty much everything, from our medicine to climate science. What we've seen here is just how much hidden engineering goes into getting just one single number right. And it makes you wonder, in our world of big data and endless statistics, what other unseen guardians are working behind the scenes to make sure the numbers we all trust are actually true?